Welcome to AISC's live webinar, part 2 of our two-part series, Designing Structural Stainless Steel. Part 2 will be presented by Nancy Badu, and my name is Patrick Newman. I'm with the AISC Continuing Education Group, and I'll be moderating today's presentation. I would like to introduce today's speaker. Nancy Badu is a chartered engineer, fellow of the Institution of Civil Engineers, and Associate Director of the Steel Construction Institute in the UK. Throughout her 26 years at SCI, she has worked on many research projects studying the structural performance of stainless steel, as well as being active in disseminating design guidance for architects and engineers through publications, seminars, and online design tools. She chairs the European Technical Committee responsible for the Stainless Steel Eurocode, and she authored the AISC Design Guide 27 on structural stainless steel. Also attending is Catherine Hauska from TMR Stainless. Catherine presented part 1 last week, and she is attending today, and we may hear from her during the question and answer session. So with that, I'll hand it over to you, Nancy.
Thank you very much, Patrick, and a warm welcome to everyone for this webinar. I'm presenting from the Steel Construction Institute in the UK today, and SCI promotes the effective and efficient use of steel in construction through writing design guides, software, developing standards and specifications, and carrying out research and development activities. This is an overview of the material we're going to cover today. Firstly, I'm going to briefly introduce the scope of the design guide, and then we'll have a quick revision of why and how you might use stainless steel in construction. Then we're moving on to look at the actual design rules for structural stainless steel, having explained why it's necessary. So we'll look at design rules for members and connections, and finish looking at the structural fire resistance rules. This is the design guide, DG27, which covers structural stainless steel, and it was published 6 months ago in September. It's freely downloadable for AISC members, and for non-members the PDF can be purchased for $60. What's in the design guide? Well, here's the first part of the table of contents. The chapters I'm showing in purple were chapters that Catherine Hauska explained last Thursday at the first part of this webinar. And at the webinar, you'll remember she talked about materials issues and durability and grade selection, and then she also talked about fabrication and welding. So I'm not going to cover those issues again. I'm going to concentrate more on the structural engineering issues covered in the design guide. There are a couple of appendices in the design guide. I'll mention Appendix A, the continuous strength method. Appendix B gives a commentary to the design rules if you're wanting to look in deeper and find the background to them. And then there are 6 design examples which illustrate the application of the rules, as well as symbols and references. So, a quick revision, because this was discussed last week. Why would you want to use stainless steel in construction? Well, the main reason is because of its corrosion resistance and its long life. Stainless steel doesn't need any special coating because it has a layer of chromium oxide on its surface that forms spontaneously in the presence of air. So it's ideal for structures where you want low or no maintenance. And of course, architectural requirements often require an attractive metallic exposed surface finish, so that would be another reason for specifying stainless steel. But you may not be so familiar with the fact that stainless steel has good impact and blast resistance properties. Sometimes hygiene properties are important if, for example, you're having applications in contact with drinking water, and that's another reason why stainless steel might be specified. It has very good cleanable surface. And also, some stainless steels, the austenitic family, are non-magnetic. So occasionally in medical or defence applications, that might be an important design criterion. I have 4 slides now to show you of some photos of structural applications of stainless steel. And this first slide shows you applications where stainless steel has been specified because the application is in an aggressive environment. And this top image here is where we have some structural eye sections that are used in a pulp and paper plant where we have a very corrosive environment. And this photo beneath, that's actually Longwood Gardens, a conservatory there in Pennsylvania. You can imagine, you wouldn't say it was an aggressive environment, but it was warm and moist. And so the carbon steel roofing members had to be replaced with stainless steel. And my third photo is in a tunnel. Highly durable materials are needed in corrosive environments that you would find in tunnels. Maintenance is very expensive, and of course there are very severe consequences of a structural failure or fire. So stainless steel might be used for supporting the lining or framework or maintenance walkways and fittings and fasteners. My second slide of photos shows some applications where stainless steel has been selected partly because of its aesthetic characteristics. And these types of applications tend to be canopies or entrance pavilions. This photo here is a skyscraper in the City of London where stainless steel forms an entrance pavilion. And these are canopies leading down to subways in New York. And this slide here is a roof leading into a station in Belgium. My third slide shows a typical cladding support, fittings and fasteners. Stainless steel is often used to support glass curtain wall systems or perhaps cable net walls, and also used for fittings into wood and masonry. Perhaps these fittings might be inaccessible or difficult to replace, so a highly durable material is needed for them. And the final slide of photos shows some applications where the impact and blast resistance of stainless steel is important. This photo here is taken in Geneva, and it's a security barrier with very high impact resistance outside the United Nations offices. And the slides over here show stainless steel being used in a blast wall on an offshore platform. Let's move on now and discuss why stainless steel needs its own design rules in the first place. Looking at the stress-strain characteristics, you can see carbon steel shown in blue, has a sharply defined yield point with a plastic yield plateau. Stainless steel, however, exhibits gradual yielding with high strain hardening. So you can imagine the first challenge is really, what is the yield strength that you use for design? And the convention that is adopted worldwide for materials which have these non-linear stress-strain characteristics is to use the 0.2% offset yield strength. And this figure shows you how you calculate the 0.2% offset yield strength. You travel along here the strain axis to a 0.2% permanent strain, and then you draw a line parallel to the initial elastic modulus, and where that hits the stress-strain curve, that is the value that you take for your design strength. On this graph, I am comparing the stress-strain characteristics of two families of stainless steel. So this lower graph, which I've marked 304 and 316, this is a typical graph that you would expect for the austenitic family of stainless steels. And this higher graph is a typical curve that you would expect for the duplex stainless steels. And I've also shown a grade 50 carbon steel A992 stress strain characteristics. And here we've marked where we calculate the 0.2% offset yield strength. So I've put really the same information here in a slightly different format, comparing the austenitic, the duplex and the carbon steel. But I've added too the fact that the initial elastic modulus or Young's modulus is more or less the same. For the austenitics we take a value of 28,000 KSI compared to carbon steel and duplex, which is 29,000 KSI. And I've also added on this slide, because we were asked this last week, that the density of stainless steel is very similar to the density of carbon steel. It varies a little between the austenitics and the duplexes, but it's all between 485 and 500 pounds per foot cubed. How does the nonlinearity actually impact the behaviour of a structural member? Well, firstly, it leads to different limiting width to thickness ratios for local buckling. And it also affects member buckling behaviour, both in columns and for unrestrained beams. And finally, for beams that are loaded quite heavily, you would expect greater deflection. So what's the impact on the buckling performance? Well, if we look at columns that have low slenderness firstly, these are columns that would attain or even exceed the squash load, and so the benefits of the strain hardening would be clear, and stainless steel would behave at least as well as an equivalent carbon steel column. At the other end of the scale, if you have a high slenderness column, your axial strength is low, the stresses are low, and you're in the linear region of the stress-strain curve. So stainless steel would behave similarly to carbon steel. And in the intermediate slenderness range, your average stress in your column would lie between the limit of proportionality and the 0.2% offset yield strength. So this is the region where the stainless steel column would be less strong than the carbon steel column. It is worth explaining a little more about the concept of strain hardening, and sometimes it's called work hardening, or people might call it this material is cold worked. So it simply means that it's the increase in strength by plastic deformation. It's caused by operations like cold forming, roller levelling, and during fabrication. It can actually have quite a remarkable impact on the strength of certainly austenitic stainless steels. During the fabrication of a hollow structural section, you might expect the 0.2% offset yield strength to increase by about 50% in the corner regions which have been highly strain hardened. Now the ASTM Spec A666 actually covers stainless steel in the cold worked condition, and you can specify this when you're buying it, and it's defined as quarter hard, half hard, etc. You'll appreciate that strain hardening is not always useful. When you're fabricating stainless steel, it means you need more powerful equipment, stronger tools, greater forces. And strain hardening can also reduce ductility. However, the ductility of stainless steel is so high anyway, that's not usually a problem. A couple of other aspects of the stress-strain characteristics need to be mentioned, and that is, in stainless steel, you do observe some non-symmetry between tensile and compressive behaviour. And additionally, there can also be anisotropy, and this describes the difference in behaviour between coupons which are parallel or transverse to the rolling direction. Now these two phenomena, anisotropy and non-symmetry, they increase with the level of cold work. So I show here some stress-strain curves for an austenitic grade in the cold worked condition, a quarter hard. And you can see that depending on whether the coupon is longitudinal or transverse, or whether it's tested in tension or in compression, that the stress-strain characteristics do differ. But the good news is that for the types of structural sections that we're dealing with in the design guide, they're not made from heavily cold-worked material. And so the differences in the stress-strain behaviour due to non-symmetry and anisotropy are not large at all, and it's really just the non-linearity which has the greater effect. However, these phenomena are more significant in the design of the lighter gauge material, and these are covered by the AISC SEI specification 8, which is the specification for cold-formed stainless steel structural design. Let's move on to look at the ductility and toughness of stainless steel. Just a quick definition for you. Ductility is how much a material can be stretched without breaking, and the toughness is how much a material can absorb energy and can deform plastically without fracturing. And the area under the stress-strain curve is the quantity of absorbed energy. So I've plotted here the stress-strain curves for the full until failure. strain range. So you can see that the austenitics do have a very, very high ductility, and duplexes less so, but still pretty high, around 40%. And you can also see that the area under the stress strain curve is very high. And this is what gives the stainless steel family very good resistance to impact and blast, because a lot of energy can be absorbed. So this photograph shows the damage to the stainless steel rail car was contained within localized areas, just the front part, because of the energy absorption properties. And this is due to the very high ductility and the high rate of strain hardening. What's the toughness then at lower temperatures, sub-zero? Well, for the austenitic family, there's no ductile to brittle transition. The material remains ductile down to very, very low temperatures. The duplexes are a little more similar to carbon steel when it comes to ductility at low temperatures. They generally have good low temperature toughness. The lean duplexes, and this term lean means less highly alloyed, they show a minimum of 30 foot-pound force in the base and weld metal at temperatures down to minus 58 degrees Fahrenheit for a 1.2 inch plate. And the standard duplex, say 2205, has even better toughness. And these materials, these duplexes, they're used in pressure vessel applications where toughness has to be demonstrated. The duplexes are also being used increasingly in structural bridge elements, and also because of the exposure to cold temperatures, toughness is an important design criterion there. So what's the response to seismic loading? Well, you can see that the higher ductility leads to the ability of stainless steel to sustain more load cycles, and this means that there's greater opportunity for hysteretic energy dissipation under cyclic loading. Secondly, the strain hardening enhances the development of large and deformable plastic zones. And thirdly, stainless steel has a stronger strain rate dependency than carbon steel. What that means is that if it's subject to a high-speed impact, then its strength increases at a greater rate than if it was subject to an impact at low speeds. And this dependency is greater than what you would measure for carbon steel. So that also is a benefit in responding to seismic as well as blast loading. Now I'm going to review what design specifications are available for structural stainless steel. Since the 1960s, a great deal of research has been carried out measuring the structural response of different stainless steels, hollow sections, welded sections, under ambient temperatures, in fire, fatigue loading, mechanical connections, welded connections. And this research predominantly started in the States, and then over the years a lot has been carried out in Europe, South Africa, Australia, and more recently a great deal is happening in China. And I put this logo at the bottom here because since 1998, we have held 4 expert seminars where we gather together researchers working in the field of structural stainless steel, and we share our work, we find out what everyone's doing, we discuss with industry what the priorities are, and we discuss code developments. We get the code writers together and we discuss and compare the structural design standards. So, this slide shows the different structural design standards that are available worldwide. As I said, there's an American specification for cold-formed stainless steel members. That was first published, I think, in 1968, and there have been a couple of revisions since then. Then the South African and Australian and New Zealand standards bodies took that work and modified it slightly to prepare their own specifications for cold-formed members made of stainless steel. And in Europe, we work to Eurocodes now. Eurocode 3 is the steel design Eurocode, and part 1.4 is for stainless steel. Now that has a wider scope. That covers cold-formed as well as welded and hot-rolled members. In Japan, for some time now, they've had specifications for cold-formed and welded stainless members, and they are now preparing one for civil engineering structures, including rebar. And finally, in China, there is a standard shortly to be released which covers, I think, cold-formed and welded members. So, moving now to look at the scope of the rules in Design Guide 27, we cover hot-rolled or welded and welded open structural sections. So those are sections like I-shapes, channels and equal angles. We also cover hollow structural sections in thicknesses for all these sections greater than 0.125 of an inch. The design rules are applicable to austenitic and duplex stainless steel, but also for precipitation hardening stainless steel for the bar, tension bar and fastener applications. And the rules are presented in both the LRFD and ASD design philosophies. On this slide, I've summarized the actual grades of stainless steel that are covered by the guide. So in green, they're the austenitic stainless steels, and you can see here we have the design strengths, or the 0.2% offset yield strengths, and here we have the ductility, the elongation. Now, the grade names are a bit confusing. The ones in black are the UNS systems, the Unified Numbering System, and the ones in red are the popular naming. So you'll hear me saying something like 304 or 316. Now, in pink, these are the duplex stainless steels, and I've already explained the difference between a lean and a standard. The lean duplexes, they are cheaper because they're less highly alloyed, and you see here the strengths are considerably higher than the austenitics. This is a newer family of stainless steels, and I think one that has great potential for further application in structures because of its higher strength. Then in blue, I've put here the precipitation hardening grades, which are very high strength for use in tension rods and fasteners, and for comparison, carbon steel here. Now, there are quite a lot of other grades of stainless steel, so I've put a provision in the design guide that the design rules can also be applied to other types of austenitic, duplex and precipitation hardening grades, providing they have an elongation of 20% or more. But the guidance in the design guide dealing with durability and fabrication wouldn't necessarily apply to them, so you might need some specialist advice for that. Comparing the scope of the design guide with the scope of the full AISC specification for structural steel for buildings, the design guide covers the commonly encountered structural shapes and load scenarios, and it doesn't cover every scenario given in AISC 360. This has been around since the 1920s, so we've got a bit of catching up to do on the stainless side. And additionally, some of the rules aren't really relevant for stainless steel because it would never be used in that type of application. So the design guide, it doesn't give rules for members in flexure which are angles and T's, and nor for members that have slender webs in flexure. It doesn't cover unequal leg angles, and nor does it cover slender cross sections in equal leg angles or round hollow structural sections. And these are some other parts of the chapters where we don't yet include design rules. For example, tension field action isn't covered in the chapter on shear, and we don't deal with composite members yet, although stainless steel is used fairly commonly for applications, for example, forming a hollow structural section with concrete inside. That's a fairly typical application of structural stainless steel. The design guide clearly states the scope of the applicability of each of the stainless steel rules, so it's quite clear what the design guide is covering and what it isn't. I'd like to explain how the design rules were developed. We started off by looking at the carbon steel rules in AISC 360 and comparing those design rules with all the stainless steel data that we had collected from laboratory tests on beams and columns, etc. And then, where necessary, we modified the AISC rules as simply as possible to suit the stainless steel data. And then we calculated the resistance factors to use with the stainless steel rules. So in order to calculate these resistance factors, we carried out quite a comprehensive reliability analysis following the protocol that was used for AISC 360. So I've put on this slide, this was the target reliability indices we used, 2.6 for members and 4 for connections. And from these expressions you can see that the reliability index is related to the, this is the mean value of resistance, and this is the mean value of the load effects. And these are the coefficient of variation of the resistance and the load effects. And from that expression you can calculate the resistance factor. You can see these symbols here. Now these are the random variables that reflect uncertainty in the material properties, that's M. In the geometrical properties, that's F. And P represents the uncertainties in the design assumptions. So what we did was we gathered together statistics on material data and the variations in the thickness and breadth and depth of sections, and we were interested both in the mean values, for example the mean of the 0.2% offset yield strength, as well as the scatter, because they both affect the resistance factor. In an ideal world you want a high mean and a low scatter. So we developed this database of the test results that had been carried out, and that enabled us to go through each failure mode in turn to derive the resistance factors. And that process is explained in full in Appendix B. And the outcome of that work was that it was okay to use the carbon steel resistance factors in almost all cases. In fact, in some cases we could have justified even higher resistance factors, but we elected to use the carbon steel factors for now, except for round hollow structural sections where a slightly lower resistance factor was needed, 0.85, and for fillet welds also a lower resistance factor is needed. These are the design topics that we're going to run through now during the remainder of this webinar, and I put on this table a quick comparison of the chapter in the design guide and the chapter that you'll be familiar with in AISC 360. So I'm just picking a few highlights really from these chapters to illustrate the design rules. In a nutshell, designing structural stainless steel, you use the same approach as for carbon steel, but you make sure that you're using the correct 0.2% offset yield strength for the type of stainless steel you're designing, and you would need to use lower limiting width to thickness ratios for local buckling and different buckling curves for your columns and unrestrained beams. A reminder, these are the design strengths you would be looking at: austenitics, an FY of 30 KSI generally, and duplexes between 58 and 67 KSI. So you'd see the same principles would apply that apply to designing high strength carbon steel. It's not always going to be possible to take full benefit of the higher strength if, for example, your design is governed, say, by deflection, or if local buckling kicks in. Firstly, looking at design requirements, the guidance is generally follow the carbon steel rules for the elastic analysis of frames, but use the strengths that you're calculating from the design guide. And you should bear in mind that second order effects in sway frames, they might become more significant if the stainless steel is stressed into the nonlinear portion of the stress strain curve. Unfortunately, there's no guidance yet on plastic analysis of stainless steel frames. So, classification of sections for local buckling. As I just said, same approach for carbon steel, lower limits generally. And on this table, I have tabulated carbon steel next to stainless steel. So let's look at a couple of them. This top one, so these are unstiffened elements, so they're flanges of rolled eye-shaped sections. Carbon steel limit 0.56, root E over Fy, stainless steel 0.47. And if we look for the stiffened elements, we can see the webs of doubly symmetric eye-shaped sections and channels, 1.49 for carbon steel, 1.24 for stainless. And down to the round hollow structural sections, 0.11 versus 0.10. Moving to design of members for tension. Well, no change, as you would expect, from the carbon steel expressions. Here we have the nominal strength given for tension yielding in the gross cross-section and for tension rupture in the net section. However, it's worth pointing out that you may get larger deformations. Well, you would get larger deformations because of the high ratio of Fu, the tensile strength, to Fy. And for austenitics, this ratio can be around 2.2. The ratio for duplexes is more or less the same as you're familiar with for carbon steel. So, for structures that might be sensitive to deformation at serviceability, the design guide does include an extra check, and this is what's given here. For tensile rupture in the net cross-section, there is an extra check where the nominal strength is limited by the yield rather than the ultimate strength. Moving on to compression, Chapter 5 of the design guide. So firstly, let's look at the expressions where you don't have slender elements. No change to the equations E31 and E34, which give the nominal compressive strength and the elastic buckling stress. However, there are modifications to equations E32 and E33. The philosophy I adopted in this design guide was to always keep the shape of the carbon steel equations and simply to modify the coefficients, hoping that this would make life easier for designers and easier for developing software from the carbon steel software. So this is equation E32, and you can see that the coefficients have been reduced, 4.71 reduced to 3.77. Likewise, equation E33, the coefficients have been reduced again. Now let me show you what this actually looks like. This is the buckling curve. I've plotted the reduction factor against a slenderness that actually normalizes the strength and elastic modulus. And you can see in blue I have plotted the AISC carbon steel curve. That's that curve there. And then in black is the stainless AISC design guide curve. And then just in case you're interested, I've put in the Eurocode stainless steel curve. And I've shown the data points so you can see how the actual test results compared with the design curves. Now, how we deal with compression members which have slender elements is exactly the same as those without slender elements, as you would expect. So these two equations, they're the equivalent to E32 and E33, and they simply have the Q factor, which is the net reduction factor, which is what you need for slender elements. But the reduction in the coefficients is exactly the same. 4.71 becomes 3.77. And likewise for equation E73, the same numbers with the Q factors. So firstly, let's deal with unstiffened elements. So these are flanges. And here it's necessary to calculate the factor QS. So it was necessary to modify the carbon steel expression to join up with the section classification limits that I showed you earlier on. So that was equation E74, this is E75, and likewise E76. So these are all expressions where the coefficients have been modified in order to calculate the QS factor. Let's look at stiffened elements. So these are webs, and again some modification is required for stainless steel to join up with the section classification limits I showed you. For the stiffened elements, you'll remember that you calculate an effective length or effective breadth B, and from that you calculate an effective area, and you calculate a QA factor, which is the ratio of the effective area to the gross area. Moving on to the design of members for flexure, there is some modification required when it comes to lateral torsional buckling. And a lot of the expressions still apply, but some modifications I will show here. So the lateral torsional buckling curve, the part that's given in equation F22 is modified for stainless steel. That is the expression there for the nominal flexural strength, Mn. And then again modifications are required to the equations F23 and F25. What does it look like? This graph I've plotted against the length on the horizontal axis and the reduction factor on the vertical axis. And here the carbon steel lateral torsional buckling curve. The black line is the AISC stainless curve. And again, I put in the Eurocode curve just for your interest. And finally, on members in flexure, there are some modifications just for the square and rectangular hollow structural sections and box-shaped members. So firstly, for flange local buckling, some modifications are required. And again, this is to join up with the section classification table. Those limits were all derived from tests on actual structural members. Secondly, this modification is required to equation F74. And finally, a modification to equation F75, which is the web local buckling expression for the square and rectangular hollow structural sections. A few slides about deflection. You can see that the fact that the stress-strain curve is nonlinear means that the stiffness of stainless steel does reduce as the stress increases, and the amount of reduction all depends on how high your stress level is. But it will lead to some increase in deflection, and the process to estimate these deflections is to calculate the secant modulus, which I've shown on this diagram. It's the one here in light blue, ES. And we just recommend a very conservative procedure of calculating the secant modulus for the maximum stress in the member at the serviceability limit state. So in order to calculate the secant modulus, you have to use this equation, which is taken from the Ramberg-Osgood model. And you can see the secant modulus, ES, is related to the initial elastic modulus, Young's modulus, and also related to the serviceability design stress, F, and to this parameter N. Now N is a material constant, and it's called the Ramberg-Osgood Parameter, and I'll show you on this slide exactly what it is. It is a measure of how nonlinear the stress-strain curve is. So if you look at this black line, this is a continuous black line here, this is an N value of infinity. So there's no strain hardening, and we often simplify the carbon steel stress-strain curve like this, as a bilinear elastic plastic stress-strain curve. And then the curves in red and green, etc., they show materials that have decreasing values of N. So you can see here the blue curve has an N value of 5. So as N decreases, so the nonlinearity increases. And this behaviour is all defined by the Ramberg-Osgood model. So for austenitic stainless steels, you'd generally be thinking of them having an N around 5. So it would be described by this. And duplexes, they're a little more like carbon steel, so they'd be coming down to something between 7 or 8 around here. So you calculate your secant modulus, and that enables you to estimate your deflection. So I've plotted on this table, it's like a worst case scenario, and it assumes that the ratio of your stress is 0.6, so that your stress at the serviceability limit state divided by your design stress is 0.6. So you'd be unlikely to go higher than that. So what impact does that have on our modulus? For the austenitics, you would see a secant modulus of about 23 to 24,000 KSI. So that's a reduction of 15%. However, for the duplexes, because they have a higher strength, and that all goes into the formula for calculating the secant modulus, you have a much smaller reduction. I think it's about 5% here. Moving on to design of members in shear. Now the rules for carbon steel in Chapter G in AISC 360 can be adopted. I've mentioned that tension field action is outside the scope, as is shear buckling of round hollow sections. Now I would like to flag up that in Chapter G, for webs of rolled eye-shaped members, you'll remember that if the H/T value is low, you can actually use an increased resistance factor value of 1. But we haven't included this allowance in the design guide since we had no specific test data to justify that. So the resistance factor of 0.9 applies. And then for design of members for combined forces, that's covered in Chapter 8 of the design guide. Again, the rules for carbon steel can be adopted. But of course, you have to use the resistance factors that are relevant to stainless steel in members in compression and in flexure. So I mentioned there was an appendix, and this is Appendix A, which gives you the opportunity of a less conservative design method. It only applies to rectangular hollow sections and to eye sections, and for members with a low cross-section resistance. Sorry, with a low cross-sectional slenderness. That's what lambda bar P is. But it does give you 10, 15 or so percent increased resistance by taking into account the benefits of strain hardening. Just before we move on to connections, I'd like to summarise the design of stainless steel members. As you've seen, very similar to carbon steel members. Limiting width to thickness ratios are lower, the buckling curves are also lower, and deflections may be slightly higher. Now, in the remainder of our time for this webinar, I'm going to cover some aspects of design of connections and then also structural fire design issues. So, we'll quickly look at welded connections, bolted connections, then the affected elements of members and connecting elements, flanges and webs with concentrated forces, and then a slide on fatigue. When it comes to the design of welded connections, the carbon steel rules can be applied to stainless steel. In general, the rules about effective area, the strength of groove, fillet, plug and slot welds, the design expressions can also apply. Just a note that for austenitics, this ratio of Fy over the tensile strength of the filler metal is low. So it's more likely that the base material, the base metal strength, will control the weld strength for fillet and partial joint penetration groove welds. I'm sure Catherine mentioned last week that it's quite possible to weld stainless steel to carbon steel. It happens a lot, and you just need to make sure that you use the right filler metals and follow the right welding procedures for that. The resistance factors for welded joints are slightly lower, and this is mainly due to just fewer test data we had to analyse. Moving on to bolted connections, a couple of words before we look at the design rules. And one point is that the corrosion resistance of the bolts and the parent metal should be similar. In fact, it's important that the bolt should be at least as corrosion resistant as the most corrosion resistant of the metals being combined. So what I mean by that is, if you're joining a plate 304 to a 316 plate, 316 is more corrosion resistance. So your bolt should have a corrosion resistance equivalent to a 316 grade of stainless steel. Now, we covered last week the fact that you should use stainless bolts to connect stainless members. You don't want to use carbon steel bolts in stainless members. And also you can use stainless bolts in other metals to connect galvanized steel and aluminium members, for example. There are 4 or 5 specifications covering the mechanical properties of stainless steel bolts, and in this webinar I've just put one table up that shows you the tensile strength. So this is taken from ASTM F593, and it gives the tensile strength for bolts 304 and 316 in various conditions for various diameters. And additionally, it includes precipitation hardening stainless steels also, you can see, with very high strength. I just refer to again to this ASTM A1082, which is a new one that includes duplex fasteners. So what are the design rules? Well, the rules for carbon steel bolts in clearance holes generally can be safely applied to stainless steel. So these are talking about the bearing type of connections. So you have Rn, which is your nominal tension or shear strength. And these are expressions that you will have seen in your table, I think J32 in AISC 360. The expression for the nominal tensile strength, 75% of Fu, where Fu is the specified tensile strength given in the ASTM that you're using the bolts from. FNV, this is the nominal shear stress. And as with carbon steel, we have two expressions with the threads not excluded and the threads excluded. When it comes to bearing, there are some special rules for bearing resistance, and this is simply to limit the deformation due to the high ductility of stainless steel. So if it's important, there is an expression for the nominal bearing strength where deformation at the bolt hole at service load is a design consideration. And there's an additional expression where deformation at service load is not a design consideration. So these differences are simply because of this rather high ratio of Fu over Fy for stainless steel. For austenitic stainless steel, I should say. For duplexes, there's really not much difference. Looking now at the design rules for affected elements of members and connecting elements. The guidance in AISC 360 J4 applies. But of course you use the stainless steel resistance factors and the stainless steel buckling curves. For flanges and webs with concentrated forces, the guidance in the specification section J10 applies. Now currently there are no design rules for stainless pre-tensioned bolts. So what I've said before has been for bolts that are the bearing type of connections. And for this reason you should carry out tests. They are used in structures around the world, but in order to validate the strength from them and the correct pre-tensioning procedures, you should carry out tests. Now it's important to do the pre-tensioning in the right way, because if stainless steel bolts are very highly torqued, then you can have this phenomenon called galling. Now galling isn't thread stripping, it happens when you have surfaces that are under load and in relative motion, and it can be called cold welding, but some sort of local adhesion occurs. And it's not just a stainless issue, it happens with aluminium and other alloys which have this protective oxide film for corrosion protection. But what it results is a seizure. And so if you're not wanting to undo the bolts, it's fine, no problem. But if you are wanting to undo the bolts, then it can be an issue. So the design guide gives a few ways of how you can avoid galling. One of the ways is to lubricate the internal or external threads. Another way is to make sure that the threads are as smooth as possible, or to use different stainless steel types with different hardness levels for the bolt and the nut. Another issue that needs to be considered for the use of pre-tension stainless bolts is the issue of time-dependent stress relaxation. which does happen to a certain extent for the austenitic and duplex families. When it comes to the methods, you should bear in mind that a carbon steel DTI won't give a correct prediction of the tension in a stainless bolt. But the other methods that you would be familiar with for pre-tensioning, like the turn of the nut method, would be able to be used on stainless steel bolts. So what about fatigue strength? The fatigue behaviour of welded joints is really dominated by the geometry rather than by the particular type or grade of steel or stainless steel. And tests have shown that the performance of stainless steel welded joints subject to fatigue loading is really at least as good as that of carbon steel. So we say in the design guide that the carbon steel rules can be applied. And conventional fatigue improvement techniques can also be applied to stainless steel. Final section of the webinar is looking at fire-resistant design. And I have put here a couple of photos of some column tests that we've done. Loaded up a column and put it in a furnace just to prove that these design rules are based on actual test results. So firstly, what do you need to know in order to calculate the fire resistance of a structural member? Well, you need to understand the thermal properties at high temperatures, which will help you calculate the rate of temperature rise, because you'll need to know what the column will be doing after 15 minutes, 30 minutes, etc., exposure to a fire. And then you need to use the mechanical properties in order to calculate the strength of the member at elevated temperatures. I have put on this slide an excerpt from AISC 360 from the commentary to Appendix 4, which gives the classic heating up equation. And this equation, you've got your delta TS here on the left hand side, and it tells you how quickly your section is going to heat up. This parameter A is the heat transfer coefficient, and this ratio W over D, is the weight per unit length divided by the heated perimeter. So you can see that if you have a high W over D, then your rate of heating up will be low. But if you have a low W over D, then your rate of heating up will be high. So the convective heat transfer coefficient is given at the bottom of the slide, and that is applicable to stainless steel as well as to carbon steel.
Are you there?
Yes, I'm still there, but my webinar is not. So I'm just moving over.
Can you move the slides?
Yeah. Well, if you can move the slides, that would be good, because I can't anymore.
Tell me when you need it moved.
Yep, I'd like it moved now to 96.
Okay, there we go.
Right. Let me just have to look at the paper now. So The thermal properties of stainless steel differ slightly to those of carbon steel, and I've put on this slide a comparison of the emissivity. The emissivity is the relative ability of its surface to emit energy by radiation, and it's the ratio of energy radiated by a particular material to the energy radiated by a black body. So a black body has an emissivity of 1, whereas generally other materials have emissivities less. And you can see here that on this slide I have compared the emissivity of stainless steel 0.4 to carbon steel 0.7. Stainless steel is a bit shinier, so you'd expect it to have a lower emissivity. And the specific thermal capacity of the two metals is more or less the same. And the outcome is that stainless steel heats up more or less at the same rate as carbon steel. Next slide, please. Other thermal properties. On this slide I've shown the thermal conductivity. Austenitic and duplex stainless steels have a much lower thermal conductivity than carbon steel. It's about a third of the value. And this can be good and it can be bad. It can be good when you're wanting to minimize thermal bridges. That's when you want a low conductivity. For example, when you're connected balconies to buildings, where it's important to minimize the thermal bridge, stainless steel is sometimes used in this way. But it also can be a disadvantage because you can get heat gradients, for example, when you're welding, because the heat's not conducted away so quickly. Slide 90 shows the mean coefficient of thermal expansion, and it compares the austenitics in red with the duplex and the carbon steel. So again you see some differences. This is due to the different microstructure and alloying content. Austenitic stainless steels do expand at a greater rate than carbon steel. So slide 91 just talks a little bit more about the impact of thermal expansion. Of course, in a structural frame, restraint will exist. And so if you've got additional forces due to your stainless steel member trying to expand more as the temperature rises, then this can be bad news and can lead to a premature failure. So you have to be careful with detailing of your connections to take into account the different thermal expansion of stainless steel. And it's also necessary to take measures to minimize weld distortion because of the low thermal conductivity and the high thermal expansion. And the design guide gives you various techniques. I'm back on Ready Talk now. The design guide gives you various techniques for how to minimize weld distortion. For example, using symmetrical joints, ensuring good fit up, reducing where possible the extent of welding, etc. This graph compares the strength as it degrades with temperature for the austenitic, duplex and carbon steel. So this blue line is carbon steel, retains its strength right up to temperatures of approaching 1000 degrees Fahrenheit, and then it drops quite rapidly. The orange line is the austenitic grade 316, and then the red line is 304. Rather different characteristics, losing strength fairly rapidly, but then at temperatures above, say, 1100 degrees Fahrenheit, then the strength is retained better. This graph compares the way the stiffness, Young's modulus, degrades with temperature. And you can see stainless steel is shown in red and carbon steel in blue. So quite a bit of difference here, that stainless steel retains its stiffness more or less throughout the whole temperature range in a better way than carbon steel. And there are implications on this behaviour. If we look at, if you could move me along to slide 102, I've lost the connection again. Slide 102 compares the behaviour of carbon and stainless steel columns in fire, and we generated this slide by doing some finite element analysis. And you can see they're equivalent columns, and we've compared their performance at temperatures of 750 Fahrenheit, 112 Fahrenheit and 1472 Fahrenheit. And you can see that at the lower temperature the columns behave more or less the same, carbon steel and stainless steel. But as the temperature increases, then the advantage of the stainless steel retaining its stiffness becomes quite apparent, and the stainless steel column shows some superior performance at these higher temperatures. Moving along to slide 95, design rules for fire resistance. Basically, you do exactly as you would for carbon steel. These are the rules given in Appendix 4 of AISC 360, but you would use the stainless properties at the elevated temperatures, which I've just showed you, and you do need to make a couple of modifications to the carbon steel design expressions for columns and beams. We're almost out of time now, so I'm just going to show you in slide 96 what we've done for columns in fire. And the recommendation here is that you use the room temperature buckling curve with elevated temperature properties, and exactly the same expression as you would for carbon steel for the elastic buckling stress. But this time the FE is related to the temperature. And it's related to the temperature by using the elastic modulus at the temperature of interest. So slide 97 just shows the difference between the stainless and the carbon steel design expressions for columns in fire. So for stainless steel, you're using the room temperature buckling curves, but they're modified to use the properties for strength and stiffness at elevated temperatures. Whereas for carbon steel, they have derived a specific fire buckling curve, which is given in Appendix C. So moving on to my final slide, which is slide 98, and I summarise as I finish. The nonlinear stress-strain characteristics of stainless steel mean that some different design rules do apply, and that's why we wrote the design guide. We've kept the design rules very simple and very closely aligned to the carbon steel rules in AISC 360 that you're familiar with. And 6 design examples are in the design guide to illustrate the application of these rules. And I just finished with the reminder that in addition to the structural design rules in the design guide, there's quite a long section on material selection, durability and fabrication. So I'd like to thank you for listening, and I think there's some time for questions.
Yes, and thank you, Nancy. And before we get into the questions, I have a couple of polling questions that I would like to go over, and these are going to be interactive, and everyone will be able to input their answers on the computer. So our first question is, in most cases, you want to fill in the blank here, in most cases, for axial compression, the limiting width to thickness ratios for various cross-sections are blank for stainless steel than for carbon steel, higher or lower. So again, we want you to fill in the blank here. So in most cases, for axial compression, the limiting width to thickness ratios for various cross-sections are either higher or lower for stainless steel than for carbon steel. Okay, let's look at our results here. And it looks like everybody was correct. If we go back to slide 55 here, we can see, let me pull that up. We can see that a side-by-side comparison for the carbon and the stainless steels for the various cases of unstiffened and stiffened elements. And you can also find this information in the design guide. And there, in the design guide, it's in table 3-2. Okay, so we did a good job there. Now let me go to our next question. And this is also a fill in the blank. In order to estimate the deflection of a stainless steel beam, it is necessary to use the blank, either tangent modulus of elasticity or secant modulus of elasticity. Again, fill in the blank. In order to estimate the deflection of a stainless steel beam, it is necessary to use the tangent modulus of elasticity or secant modulus of elasticity. And again, here are the results, and everybody is correct. It's the secant modulus of elasticity. Stainless steel has a nonlinear stress-strain curve, meaning that the stiffness of stainless steel decreases as stresses increase. Consequently, deflections are greater than those for carbon steels, and it's necessary to use a reduced modulus to predict the behavior of members in which high stresses occur. And you can find the values for the secant modulus in the design guide in table 6-1. Okay, so now let's get into, bring us back to the concluding slide, and let's go through some of the questions that we have received. So, Nancy, since Fy is a critical factor in most design formulas, if you have material that is dual certified, for example 304/304L, do you have to use the lower yield strength, and isn't that a very large penalty?
I think Catherine can correct me if I'm wrong, but if it's dual certified, it tends to be certified to the higher strengths relevant that relates to 304. Would you like to comment, Catherine?
If it's dual certified, then actually you would have to go with the lower strength per ASTM, unfortunately. Because it is whatever is lower. But I do want to point out that often what is listed in any of the ASTM standards is the minimum for a very heavy section. And lighter sections are typically quite a bit stronger. And there is discussion currently within ASTM of possibly showing gradations for these hot-rolled sections. So you may see that in the future.
Okay, thank you. So another question on the design guide or other sources. Are there any member selection and capacity tables similar to what we have in the AISC manual available for the use in stainless steel design?
There aren't published tables in the same way as you have in your manual. Some section producers do publish their own tables. They don't go the full way in giving the section capacities, but they give section properties which are useful. But no, in Europe we have published member resistance tables, but it's not yet available for stainless steel.
Okay, thank you. Another question here on slide 22. Let me move over to that. On this slide, we show that for 304 stainless steel, we show 40 KSI. But then when we go to 41, we're using FY is 30 KSI. Why is the lower value used here?
Slide 22 is the slide that starts "Don't worry." I'm not sure what your slide you're talking about.
This is this slide that's up now. It's
yes.
I think it would be.
Well,
like
Ready Talk has crashed.
We have added slides in the front, so this would be.
Okay. So if you give me the title of the slide, then I can find it.
Stainless steel versus carbon steel. It's the graph showing the stress strain curves.
Right. So the question was, why is the strength there closer to 40 KSI? Yep. Okay.
Right.
Now the reason is that these are actual measured stress strain curves of bits of stainless steel that we stretched, and the codes give the minimum specified data, which is down to some 95% confidence level. So the graph that I'm showing in the stainless steel versus carbon steel slide, that's not to be used for design. That's actual measured material. And it's quite typical for stainless steel that you get this rather high overstrength. What you get is usually quite a lot stronger than what it says in the codes, in the ASTM for the material, particularly if you're talking about thinner sections.
Okay. That's good. So then one more. If you have to design an unequal leg angle, what design procedure would you recommend, since the design guide does not apply to the unequal leg angle?
Well, yes, I mean that's a good question, and we did anguish a bit about whether or not we should exclude them. I think you just need to make some general engineering judgment. I've laid out the facts to you about the nonlinear stress strain curve. You'll just have to make some simplifying assumptions based on what you know. I think in the compression chapter we do talk a little bit about torsional flexural buckling, but basically it's just going to have to be a conservative design assumption.
Okay. And under normal temperatures, how does the coefficient of thermal expansion compare between carbon and stainless steel?
Well, I'm not sure it has much meaning at normal temperatures, but I'm looking again at that graph, mean coefficient of thermal expansion. It is always going to be higher than carbon steel, but of course it's not going to be terribly significant until you get quite a high temperature gradient. I mean, it's one of those things that you can sometimes use to your advantage, or it can be to your disadvantage. It's similar to thermal conductivity. Sometimes you want a low conductive metal, and sometimes you don't.
Yep. Okay. What do you recommend as a separation between an exterior canopy made of stainless steel from a standing seam roof made of aluminum?
Catherine?
I'm sorry, I had to go off of mute. Could you please repeat the question?
Sure. What do you recommend as a separation between an exterior canopy made of stainless steel from a standing seam roof made of aluminum?
If the surface area of the aluminum will be much larger, which is implied possibly by the roof being aluminum, then you may not have an issue with galvanic corrosion. It's all the relative surface areas that are important. I'm assuming a canopy is small, the roof is large in terms of surface area.
Right. Okay. Actually, we're going to just do one more question because we're running out of time here. How is stress cracking currently addressed?
Catherine?
Sure. If you look at the slides from part 1, I did talk about chloride stress corrosion cracking in swimming pools. That's the only ambient temperature application in which it can occur with stainless steel. The design guide does talk about industrial applications and higher temperature briefly, and then refers users to additional data and resources. But you have to look at each environment specifically. There are charts available that provide some guidance, but you really need to know all of the parameters of the environment before you discuss whether or not it's a possibility. And help can be obtained from stainless steel industry associations, the producers. They've all done quite a bit of research.
Okay, thank you. And we do have other questions, and those will be answered, and we will get those answers to the we'll get answers to those questions for the people. So I want to thank you, Nancy, again for a very good presentation.